In this video we're going to see how integration can be used to find the centre of mass of some laminas. So integration methods are going to be useful in finding the centre of mass of a wide variety of two-dimensional and three-dimensional shapes. And to begin with, we're going to use it to find the centre of mass of some more complicated laminas, starting with the centre of mass of a uniform semicircular lamina. So let's suppose that we've got a semicircular lamina of radius r. We're going to set up the axes so that the x-axis corresponds to the diameter of the semicircular lamina, and that the y-axis is perpendicular to the x-axis as usual. Clearly, if we've got that, then we've got x bar is going to equal 0, since x equals 0 is a line of symmetry. Now, to find the y value of the centre of mass, what we're going to start off by doing is considering a small strip of the semicircle which is parallel to the y-axis and has width delta x, and we'll let x, the point x0, be the left-hand corner of this strip, and the point xy be the top left-hand corner of this strip. If the surface density of the lamina is sigma, then for this strip we can say that the mass is going to equal sigma times the area of the strip, and the area of the strip is going to be approximately y times delta x, because the strip is very close to being a rectangle of width delta x and height y. Regarding it as being a rectangle, then the centre of mass of that little strip, the y-coordinate of the centre of mass of that little strip, is going to be approximately a half times the y value of the strip. And the smaller the value of delta x, the better these approximations will be. So, for this strip, the mass is sigma y delta x approximately, and the sum of the my's for this strip is the mass of the strip times by the centre of mass, the y-coordinate of the centre of mass of the strip, so that is approximately a half y times by sigma y delta x, in other words a half sigma y squared delta x. So we've got for the thin strip that we're considering, the mass is approximately sigma y delta x, y bar is approximately a half y, and the sum of the my's for that little thin strip is approximately a half sigma y squared delta x. So for the whole semicircular lamina, what we need to do is we need to add up the masses of all of the little strips. And then, to get the exact mass, we're going to want to let delta x tend to 0. So the lamina mass will be the limit, as delta x tends to 0, of the sum of the sigma y delta x terms. But in your work for Unit 4, you will have seen that a limit of a sum like this can be rewritten simply as an integral. So the limit as delta x tends to 0 of the sum between x equals minus r and x equals r of the sigma y delta x's will become the integral between minus r and r of sigma y integrated with respect to x. In other words, that sigma times by the area underneath the curve. And of course in this case we know that the area of a semicircle is a half pi r squared, so we don't need to do an integration in this particular case. So we've got sigma times by a half pi r squared, in other words a half pi r squared sigma. For the sigma my entry, we need to add up all of the sigma my's for all of the strips. So that is going to be the sum between x equals minus r and x equals plus r of all of these half sigma y squared delta x terms. To get an exact value, we're going to need to let delta x tend to 0. So we can say that for the whole lamina, the sum of the my's is going to be the limit as delta x tends to 0 of the sum of the half sigma y squared delta x terms. The limit as delta x tends to 0 of the sum between x equals minus r and r of a half sigma y squared delta x is simply going to give me the integral between r and minus r of a half sigma y squared delta x. Now we can actually make some progress with this term, because we know that y is the square root of r squared minus x squared. So y squared is equal to r squared minus x squared. So my integral that I've got to work out, since sigma is a constant and a half is a constant, I can pull out the half sigma. So I've got a half sigma times by the integral from minus r up to r of r squared minus x squared. Well, r squared minus x squared integrated gives me r squared x, take away a third x cubed. Remember, r is a constant, so the integral of r squared is just going to be r squared times x. So doing the integration, I've got a half sigma times by the value of r squared x minus a third x cubed when x equals r, less the value of r squared x minus a third x cubed when x is equal to minus r, which ends up giving me 2/3 sigma r cubed. So I can now say that y bar for the semicircular lamina is the sum of the my's for the semicircular lamina divided by the mass of the semicircular lamina. We've shown that the sum of the my's for the semicircular lamina is 2/3 sigma r cubed. We've shown that the mass of the semicircular lamina is a half sigma pi r squared. So what I'm ending up with is that the centre of mass for the semicircular lamina has y bar equal to 4r divided by 3 pi. Now the first thing I'd like you just to do is to pause the video for a moment and try and adapt the previous argument to prove that the centre of mass of the quarter circle shown in the diagram is at the point 4r upon 3 pi, 4r upon 3 pi. When you've done that, press on with the video. If you struggle with that, then ask your teacher to take you through it when you next see him or her. The result for the centre of mass of a semicircular lamina and a quarter circular lamina are given in the formula booklet, so you don't need to remember those results. Let's try and generalise, though, what we just did for the semicircular lamina to produce a result for the for a lamina which is formed by the curve y equals f of x, where f is a positive function, between the lines x equals a, x equals b, and the x-axis. Now, again, what we're going to do is we're going to really consider very much the same sort of process as we did before, but with no line of symmetry this time. So we're going to consider a small strip of the lamina which is parallel to the y-axis and has got width delta x. We're going to have x0 be the bottom left-hand corner of this strip and xy be the top left-hand corner of this strip. If sigma is the surface density of the lamina, then for this strip, the mass is going to be sigma times the area of the strip, and provided the strip is reasonably small, it's going to be very close to being a rectangle, so we can say that the area of that rectangle is going to be y delta x. So we can say that the mass of the strip is approximately sigma y delta x. The value of x bar is going to be very, very close to x, provided delta x is small. And the value of y bar is going to be approximately a half y. And the smaller the value of delta x again, the better these approximations will be. Now, remembering that for any shape or object, the centre of mass equations can be written as the mass of the object times by the x coordinate of the centre of mass is equal to the sum of all of the mx's over the whole object. So, for the strips that we've got here, we can say that the mass is approximately sigma y delta x. The sum of the mx's for the strip is equal to the mass times the x bar for the strip, so that is going to be approximately sigma x times xy delta x, and the sum of the my's for the strip is going to be sigma y delta x times by y bar, which is a half y, so we've got a half sigma y squared times by delta x. Now we'll carry these results forward to the next page. So there we are, we've got the strip has a mass of sigma y delta x approximately. It's got a centre of mass whose x coordinate is x and whose y coordinate is approximately a half y, and we've got the sum of the mx's is approximately sigma xy delta x, and the sum of the my's is approximately a half sigma y squared delta x. So for the whole lamina, we need to take the sum of all of these sigma y delta x terms. To make it an accurate approximation, we need to take the limit as delta x tends to 0. So that ends up giving me the integral between a and b of sigma y delta x, which, provided sigma is a constant, gives me sigma times by the area of the lamina. For the sigma mx terms, what I need to do is I need to add up all of the terms of the form sigma xy delta x between x equals a and x equals b. To improve the approximation, I've got to make delta x really small, so I'm taking lots and lots of little strips. So I want the limit as delta x tends to 0 of this sum, which becomes the integral between a and b of sigma times xy. Provided sigma is a constant, we can pull the sigma outside the integration sign. So we've got sigma times by the integral between a and b of xy dx. For the sum of the my's, similarly, I want to add up all of the values of a half sigma y squared delta x between x equals a and x equals b. To improve the approximation, I've got to take the limit as delta x tends to 0 of that sum, which becomes the integral between a and b of a half sigma y squared. And provided sigma is a constant, I can pull the sigma outside the integration sign to get sigma times by the integral between a and b of a half y squared. So now I have got those three results for the whole lamina. So I can deduce that the x-coordinate of the centre of the mass for the whole lamina is the sum of the mx's for the whole lamina divided by the mass, which is the integral between a and b of xy divided by the integral between a and b of y. And for y bar, it's the integral between a and b of a half y squared divided by the integral between a and b of y. So let's have a look at this in practice. We've got a uniform lamina here. It's cut from a sheet of plastic so that the edges of the lamina are x equals 0, x equals 2 pi, y equals 0, and the curve y equals 2 plus sine x. And the first thing we've got to do is find the centre of mass of the lamina. We know that the centre of mass is has an x-coordinate given by the integral of xy divided by the integral of y, and a y-coordinate given by the integral of a half y squared divided by the integral of y. So we've got three integrals we've got to work out, and the three integrals that we've got to work out are the integral of y, which is the integral between 0 and 2 pi of 2 plus sine x, which can be evaluated to give 4 pi. We've also got to work out the integral of xy, which is the integral between 0 and 2 pi of x times by 2 plus sine x, which gives 4 pi squared minus 2 pi, and the integral of a half y squared, which is the integral between 0 and 2 pi of a half of 2 plus sine x squared, which gives 9 pi over 2. Now, these integrals you should be able to do using the methods from Maths Unit 3. So I have missed the details out here. The first one is just a straight integration. Second one will require a little bit of integration by parts. And the third one, you'll need to remember how to integrate sine squared x. So, having evaluated the three integrals, we can now say that x bar is 4 pi squared minus 2 pi divided by 4 pi, which simplifies down to pi minus a half. And that y bar is 9 pi over 2 divided by 4 pi, which gives us 9 over 8. The second part of the question says the lamina is now freely suspended from the point 0, 2. We've got to find the angle that the edge joining the points 0, 0 and 2 pi 0 make with the vertical. So, there is my diagram again with the point of suspension marked on it together with the centre of mass marked on it. When it's freely hanging from the point of suspension, if it's in equilibrium, then G must be vertically below the point of suspension, so the line PG represents the vertical. We want the angle which the line joining the origin to the point 2 pi 0 is making with the vertical, which is the angle alpha, which is the same as the angle at the point of suspension made by the vertical and a line parallel to the x-axis. And if we now consider the 2 points 0, 2 and G with coordinates pi minus a half, 9 over 8, then we can say that tan alpha is going to be the size of the y step between those 2 points, and the y step is to take away 9 over 8, so that's going to be 7/8, and the x step between those 2 points is pi minus a half. So we've got tan alpha is 2 minus 9 over 8 divided by pi minus a half, which simplifies to 7/8 over pi minus a half, or 7 over 8 pi minus 4. So we've got alpha is tan to the minus 1 of 7 divided by 8 pi minus 4, or roughly 18.3 degrees. The second example, we've got a uniform lamina L1 of mass m kilograms is constructed so that its boundaries are y equals 9 minus x squared and the x-axis. We've got to find the centre of mass of this lamina. So it's a good idea to have a sketch of the lamina. So y equals 9 minus x squared is nice and easy to draw. It meets the x-axis at x equals minus 3 and 3. The lamina clearly has the line x equals 0 as a line of symmetry, so we can certainly say that the x coordinate of the centre of mass must equal 0 by symmetry. So we've just got to evaluate the y coordinate of the centre of mass for this, so we're going to need to work out the integral of y and the integral of a half y squared. So the integral of y is simply the integral between 3 and minus 3 of 9 minus x squared, which gives 36. The integral of a half y squared is going to be the integral between minus 3 and 3 of a half of 9 minus x squared squared, which gives us 648 divided by 5. So we've got y bar, or the y coordinate of the centre of mass, is given by 648 over 5 divided by 36, which simplifies down to 18 over 5. So the centre of mass is the point 0, 3.6. A new lamina L2 of mass km kilograms consists of a quarter circle disc of radius 6. The two laminas are combined to form a single lamina as shown in the diagram. We've got, given that the centre of mass of the combined lamina is on the x-axis, we have to find the value of k, and we also have to find the distance of this centre of mass away from the origin. We know that the centre of mass of L1 is the point 0, 3.6. And we know that a quarter circle like this has got a centre of mass which is 4 times r divided by 3 pi, 4 times r divided by 3 pi. And so in this case it's 24 over 3 pi, in other words 8 over pi, 8 over pi. So the centre of mass of L2, if we just think about doing first of all a rotation by 180 degrees and then a shift of 3 units in the x direction, the centre of the mass L2 is going to be the point 3 minus 8 over pi minus 8 over pi. So we've got our two centre of masses. Now, going through with the two shapes that we've got, for L1, we know that L1 has got a mass of m, that its x-coordinate of its centre of mass is 0, therefore its sum of its mx's is going to be m times 0, which is 0. Has got the y-coordinate of its centre of mass is 3.6, so the sum of the my's for lamina, the first lamina, is 3.6m. For the second lamina, we're told that it's got a mass of km, we know that its x coordinate of its centre of mass is 3 minus 8 over pi. So therefore we've got km times by 3 minus 8 over pi for the sum of the mx's. For the quarter circle, we know the y coordinate of the centre of mass is minus 8 over pi. So therefore the sum of the my's is going to be minus 8k over pi times m. So for the combined lamina, we've got the total mass is 1 plus k times m. The total of the mx's is going to be 0 plus km times 3 minus 8 over pi. So that's just km times 3 minus 8 over pi. And the sum of the my's is 3.6m minus 8k over pi m. We're told that the centre of the mass of the combined shape is on the x-axis, so that y bar must equal 0. So we've got 3.6 minus 8k over pi times m divided by 1 plus k times m must equal 0. In other words, 3.6 minus 8k over pi must equal 0, or k must be 3.6 pi divided by 8, which is the same thing as 9/20 of pi. We can now find x bar. We know that x bar is the sum of the mx's for the whole shape divided by the mass of the whole shape. So that is going to be km times 3 minus 8 over pi divided by 1 plus k times m. But we know now that k is 9 pi over 20. So we've got 9 pi over 20 times by 3 minus 8 over pi times all divided by 1 plus 9 pi over 20, which gives me, if I simplify it as an exact answer, 27 pi minus 72 over 20 plus 9 pi comes out to be approximately 0.266. So we can say that the centre of mass is 0.266 away from the origin. So we've looked at how integration can be used to find the centre of mass of two-dimensional laminas. In our next video, we're going to be using integration to find the centre of mass of some three-dimensional shapes.